Smokes. All right, guys, here we go. So as you are engaging in what we're doing today, you got a piece of paper. Guys, I would encourage you, if you're not in the habit of doing this, title your notes. Because as you're titling your notes, what you're actually doing is writing a to-do list. So guys, the date today is the 27th. February is just about in our rear view mirror, which is amazing. But guys, again, as you're titling your notes, understand that, well, did you guys know this thing has a name? And it's not and. It stands for and, but did you know it has a name? Does anyone know the name? It's called an ampersand. I didn't know that. I just learned that. Anyway, it's an ampersand. So, guys, it says molarity and empirical formulas. And guys, understand that this and is a hard and. What you're going to find out is that molarity and empirical formulas have absolutely nothing to do with each other. So it's not like one is going to flow into the other. Guys, what we're going to do is we're going to talk about molarity conceptually, we're going to talk about molarity mathematically, and then we're going to call time out. And we're going to reset, and then we're going to talk about empirical formulas conceptually, and then mathematically, and then we're done, and you're going to have a chance to do homework. Now, guys, I mention this because you've gotten in the habit in this class of tying ideas together. It's called scaffolding, and it's what intelligent students do when they learn. Guys, I tell you that then to tell you don't try to connect the two, because they have nothing to do with each other. But guys, the thing that they do have in common is they both have moles. So this stuff that you've been learning about moles and moles conversions and everything we've been doing, we're going to bring that to bear to talk about molarity and empirical formulas. So do you understand where we're going? Let's get started. Okay, so guys, it goes like this. Molarity. Let me define it for you. Scratch it in your notes. So guys, molarity is actually a unit of concentration. So when we talk about molarity, we're talking about how concentrated is a solution. And guys, you know a lot of stuff about solutions. You know that solutions contain a solute and solutions contain a solvent. And I'm realizing I am out of solvent. Oh, wait. Oh, look. It's salt. Okay, we're good. All right, so we're good there. Good. Okay, so guys, when we talk about solutions, guys, picture everything that you know. So we know that solutions are a solute and a solvent. You can maybe even picture the water molecules attacking the salt and dragging the molecules off like little tugboats. Guys, you understand how solutions form. You understand that solute is the thing being dissolved. Solvent is the thing doing the dissolving. Well, guys, today what we're going to talk about is concentration, which simply means how much solute is dissolved in the solvent. So molarity is a measure of concentrations of solutions, and its units are moles of solute per liter of solution. So guys, you may find it easier to look at it like this. This is the definition of molarity in equation form. So molarity, which is abbreviated, capitalized, italicized M, is equal to moles of solute divided by liters of solution. So how much stuff is dissolved in how much water? So guys, here's the way we're going to do this. We're going to talk conceptually about molarity. We're going to talk about what does this all mean. Then we're going to first. Are y'all caught up with me? You okay? All right, so guys, what I did is I actually made 3 solutions in order for us to talk about molarity. Now, let me show you. So guys, these solutions all contain, can you see that? They all contain a purple solute. And the reason that I chose this purple solute is it's actually the solute that you had in your hands in station number 8. You may remember it was in the back left corner, and there was that beaker of KMNO4. and it was purple, and it was those big crystals, big purple crystals. Well, guys, what I did is I took those big purple crystals and I made them into 3 different solutions. So, guys, this solution, it's kind of cool. It looks like grape juice. So, guys, this solution is actually a solution of KMnO4, potassium permanganate. Now, guys, here's the question. This solution has a volume of a liter, okay? So that's our denominator, right? Liters of solution. Now, here's the thing. This is a 1 molar solution. Here's my question to you. How did I make it? How do you make a 1 molar solution? Or more specifically, how do you make a liter of a 1 molar solution? What did I do? How did I make it? So what's the volume of this? It's a liter. So that's the denominator. It's 1 liter. But if it's a 1 molar solution, how many moles are in here? 1. So I did not break out my mole meter and measure a mole of KMnO4. How do I know how much to put in here to add a mole? Do the math. What does potassium weigh? Manganese, 4 oxygens. Add it up and dump it in here. Guys, that's the way to think about molarity. So it's moles divided by liters, but our avenue into moles is mass. So I figured out the formula mass of KMnO4. I frankly don't remember what it was, although oh wait, I can get it right here. It is 158 grams. So guys, I weighed out 158 grams of potassium permanganate, and I dumped it in here, added a little bit of water, shook it until it dissolved, filled it up to a liter, and this is a 1 molar solution. You get the idea? So that's the molarity. It is a 1 molar solution. So guys, compare that to this. This is a 0.5 molar solution. Is it more or less concentrated? Less concentrated. How much less concentrated? Half. How did I make it? Half a mole, which would be 158 divided by 2. And then what? Dump it in here. Add some water, give it a shake, let it dissolve, fill it to a liter. You got the idea? Okay, so let's go in the other direction. This is a half molar. This is 1 molar. This is 5 molar. How did I make this? 5 moles, that's like 158 times 5. That's a pant load of stuff. But guys, I weighed out 158.5 grams of, 158.5 times 5 grams of KMnO4. I added a little bit of water. I dumped in all those crystals, got it to dissolve, filled it up to a liter, and there's my solution. You get the idea? Okay, so guys, how many times more concentrated is the 5 molar than the 1 molar? 5 times more concentrated. Now guys, here's the thing that's interesting. You can actually see it. Guys, if you look at the 0.5 molar solution, you see how you can sort of see through the neck because it's not that concentrated? Guys, this is actually one of the ways we measure molarity. In AP, we actually do these labs where we shine light through the solutions, and the more light that gets through, the less concentrated the solution is. You can actually measure that and figure out the molarity. So guys, you can see here, you can sort of see light through the solution. It's only a 0.5 molar solution. When we go to the 1 molar solution, you can now see, you can't see light through this, but you can see that it's a little bit syrupy up here at the top, right? It's getting a little more concentrated. Guys, when we go to 5 molar, this is crazy. That is 5 molar KMnO4. It almost looks like grape juice. There's no way you can see light through the neck. And guys, this is so you can see how concentrated it is, right? Do you understand the idea then about concentration and molarity? You okay? Now guys, try this. I'm going to put away the 0.5 and the 5 molar solution, and I'm going to grab the 1 molar solution, and guys, we're going to fiddle around with this. So focus on 1 molar. So this is a liter, so how many moles are in here? 1 mole. All right. Now guys, and actually, I may glove up. This stuff stains. All right, so guys, 1 molar solution, right? Here's the question. Watch close. And we're going to explore this for a couple minutes, so be ready. I can't even put on gloves. All right, so guys, 1 molar solution. So what I'm going to do is I'm going to take this 1 molar solution. Yeah, that's 1 molar. Because I'm going to divide it in half. So now we have half of this 1 molar solution still in the flask, and we have the other half of the solution now inside this beaker. So we functionally just split our 1 molar solution in half. Here's the question. What is now the concentration of the solution that remains in the flask? Can't be. Because didn't we say earlier that this contained 1 mole and 1 liter? Does it still contain 1 mole? Does it still contain 1 liter? So how can it, you're telling me it's 1 molar. How can that be if it doesn't contain a mole or a liter?
It's 1 mole over 1 liter.
Yeah. Well, it divides out to 1. Yeah, okay. Still a mole, right? A molar, a 1 mole. Does that make sense, y'all? Guys, go ahead. Yes? Yeah. I like where you're going with that, but I would be careful, because if you have 1 mole of something, it has a mass. If you have 2 moles, it weighs more. So moles are dependent upon amount. Concentration is not. Maybe another way to think about it in my brain is it's like density. Yeah, right? Because if you have a chunk of lead, we can find its density, mass divided by volume. If we cut it in half, it has the same density because we're splitting both its mass and its volume. You know what I'm saying? And guys, that's the way this works. And I think Jason did a good job of describing it mathematically. This does not contain a mole and it doesn't contain a liter, but the ratio hasn't changed because it's now half a mole and half a liter, and that's still a ratio of 1. So guys, the important thing to understand here is that simply dividing a solution does not change its molarity. This is still 1 molar. This is still 1 molar. So guys, what is the molarity of the drips that are coming off my finger? Still 1 molar. So guys, understand the concentration of a solution is not a function of how much you have. It's a function of this ratio. And you could have a liter, you could have 2 half liters, you could have drippy drips. And they all can be 1 molar solutions. Does that make sense conceptually? So guys, the question then becomes this. How do you then change the concentration? If you can't change the concentration by simply pouring a solution, what can you do to change the concentration? And guys, that's the next thing that goes in your notes. This is going to be on the test. Guys, you're actually, just a second, you're going to see questions on the test that simply ask you, what could you do to increase or decrease the concentration of solutions? Guys, this is stuff you're going to be held accountable for. Go ahead, Rachel. So yes, but so you're saying, is concentration due to amount? And the answer is yes, but it's the amount of solution and the amount of stuff that's dissolved in it. It's that ratio. All right, so guys, let's do this. And I think you probably can get 3 of the 4 answers. So guys, the question on the table is, what can we do to change concentration? There's 4 answers. 3 of them, I'm guessing you guys could come up with pretty readily. The last one is super tricky. I think you'll get it, but we'll see. So guys, first of all this, let's talk about increasing concentration. Talk about this KMNO4 solution, simply because it's messy. Let's switch. And let's go to something a little more familiar. Guys, let's go back to our good friend, table salt water. You ever wonder what's down in my magic sink? Stuff just comes out of the sink. How does that happen? I know, it really is. Did any of you see the new Mary Poppins movie? I heard it was good. Like, oh really? Okay, never mind. What I meant to say was I heard it was awful. I don't know. Don't do that. Okay, here we go. So guys, here we have, and let's make it a little salty. A little salt. And chemistry pencil. Give it a stir. All right, so guys, we now have a solution of salt water. Okay, and that has a molarity. There's no way for us to figure it out because we don't know how much salt or water is present. As Rachel said, it's a ratio of amounts. But guys, the question is this: what could we do to make this saltier? Add salt. So guys, the first thing that you can do to increase the concentration of a solution is increase the moles of solute. How do you do that? Add more solute. You gotta love it when chemistry makes sense. You just learned to make water saltier, add salt. No. Remember, you guys are in high school. You can handle these deeper thoughts. And you also learned there's such thing as a chemistry pencil. Okay, so guys, that's way number one. What is way number two to make that water saltier? We've already said add salt. What's the other thing we could do to make that saltier? Go ahead, Lauren. Yeah. Yes. Okay, and let's talk about that. When you boil it, what are you getting rid of? The water. But guys, do you understand that that's different than pouring away the water? Because when you pour away the water, why does this not make it saltier? You're also pouring away the salt, right? And we've already established that doesn't change concentration. So Lauren is saying boil it. Why does that make it more salty? Because you're removing the water, but where does the salt go? Stays behind. And that's exactly the answer. So guys, the other thing that we can do is decrease the volume. And you do that by boiling or evaporating away the solvent. And guys, understand, this is why the Great Salt Lake is so ridiculously salty. Because both of these things are happening simultaneously. When the Weber River and the Bear River and all these other rivers flow into the Great Salt Lake, they are carrying salt with them. But they don't go anywhere. Guys, the Great Salt Lake does not have an outlet. So why doesn't it overflow? It's evaporating as quickly as the water flows in. Guys, unlike Utah Lake, right? Utah Lake, the Provo River flows in and the Jordan River flows out. Guys, in the Great Salt Lake, there is no outflow. So the only reason the Great Salt Lake doesn't flood Salt Lake Valley is because it's evaporating. So we've got both going on at the same time. The rivers are adding solute and evaporation is removing water. And those two things together make the Great Salt Lake ridiculously salty. Do you get the idea? Okay, so now guys, let's go in the other direction. Let's talk about decreasing concentration. All right, guys, this is really going to be a stretch for you. You ready? Salt water. What if you want to make it less salty? Add water, right? You put water in salt water and it becomes less salty. We call it diluting. So one of the things you can do is increase the volume. If you've ever made like flavored drinks like fruit punch from that concentrate that you buy in a bottle, you know exactly what we're talking. Have any of you ever tried to drink the concentrate? Oh yeah, it's like you need a shot of insulin almost immediately. It's crazy. So guys, that stuff is super concentrated. To turn it into something you can stand to drink, you have to add water and dilute it. That's what you're doing, is decreasing the concentration. So we can increase the volume by simply adding solvent, water. But now guys, here comes the tricky one. This one's hard. You guys are smart, you'll get it, but this one's hard. Guys, what is the other thing we could do to decrease concentration? Say it again. Get rid of the solute. How? Go ahead. You could, but here's I love what you're thinking, Mauro. Couldn't we take salt water and freeze it? And if we do, then the water stays behind and the ice has no salt in it, right? The reason that doesn't satisfy the question, though, is we're not decreasing the concentration of a solution. We're creating a solid that has no concentration. Actually, the solution that remains gets saltier. Because what you're really doing is taking some of the solvent and turning it into ice, and the little bit of water that's left has all the salt dissolved in it, and it actually gets saltier. So, guys, what could we do? And I love that you got it, but we need to know how. We got to get rid of solute. We got to get the salt out of the water. Tweezers are not going to work. Guys, how do we get salts out of water? You did? Oh, wait, poop. You guys didn't do this lab. You saw me do it. Sorry, maybe this is really a stretch for you guys because you didn't do the lab. Remember when I had the beakers and I dumped them together and it formed that solid? You remember that? That solid is not dissolved in water, right? Do you remember the name that we gave it? It's a precipitate. And guys, that's the way to do this. If you could take this salt water and if you could add another substance to it that binds up with the salt and forces it to become not soluble so it doesn't dissolve, it forms a solid. That solid is no longer dissolved in water, and as a result, it decreases the concentration. So guys, the way to reduce the number of moles is by creating a precipitate. Do any of you have hot tubs? Have you ever put clarifier in a hot tub? Guys, this is kind of what clarifiers do in hot tubs. If you get too much stuff dissolved in your hot tub water, it gets cloudy. And you put this stuff in called clarifier, and it causes the stuff to precipitate. And then it's really nasty because it then all sticks to the side of the hot tub, and you got to go in and wipe it up. Or you take your friends out there and they think you're gross. But guys, that's really what hot tub or swimming pool clarifier does, is it causes the stuff that's dissolved to precipitate, and that it gets the stuff out of solution and it decreases the concentration. So guys, you good on these? With the understanding that you're going to be doing these on the test? You guys okay? Okay. So guys, with that said, oh please. That's a good question. So why is rain called precipitation if we say precipitation is this salt? So precipitation globally means to change phase. And so rain is water vapor turning into water droplets, changing phase. Precipitation in this sense is something that's dissolved turning into a solid, changing phase. And so we use the term precipitation because it generically means change phase. Is that okay? You guys good on the concepts? Are we okay? So guys, with that done then, it's now time to put on our math hats. Guys, there are two types of mathematical calculations that you're going to be doing relative to this material. In one of them, you're going to be calculating molarity. In the other one, you're going to be solving for either moles or volume. Guys, let's do the first one first. So in your notes, you just scratch down calculating molarity. And guys, it goes like this. When you solve these problems, I'm going to give you steps. This is the way these always work. So write down the steps. We'll solve one. We'll do the other. We'll talk about empirical formulas. You're going to have an aha moment. We'll do a little more math, and you'll get some homework done. You guys ready? All right. So when you solve these problems, these are the steps. We're solving for molarity, and we always set our goal first. So our goal is molarity. But guys, we're not going to write down molarity. We're going to write moles over liters, because that's molarity. Then guys, your starting point will always be mass per volume. And then guys, at that point, make conversions. What kind of conversions? The same conversions that you've been doing in the last couple homework assignments. You guys okay? Are you caught up? Did any of you print the notes? No? I didn't either, and I don't frankly remember the numbers, but we'll look them up in a second. Are you guys all caught up? Are you okay? Okay, so guys, this is the question that we're about to answer. I don't know the numbers. We'll talk in a minute. But guys, this is a salt. This is not sodium chloride salt. This is actually calcium chloride salt. A little different. This, I believe, is 225 milliliters of water. I'm not exactly sure. We'll look in a second. And then, guys, I frankly don't remember how much calcium chloride this is. We'll look in a minute. But, guys, the question that we're about to answer is if we dissolve this in here, what is the molarity? You get the idea? So we are solving for molarity. We're going to find out how much salt. We're going to find out how much water. When we dump them together, what is the molarity of the solution? So guys, what we need to know is the mass of this. We got to know the mass of the salt. We got to know the volume of the water. And when we know those, we can get molarity. So guys, let me switch slides. And here are the numbers. Oh, no, that's not. Oh, wait. Oh, sorry. Wrong sample of water. My bad. Here's the 500 milliliters of water. Okay. So, guys, the question that we're going to ask then is this. This is 7.2 grams of calcium chloride, 500 milliliters of water. Dump them together. What's the molarity? You get the idea? Okay, so let's solve it. So, guys, going back to the steps. Step number one is what? Set your goal at, not molarity, moles per liter, like so. Guys, go all the way to the right and do this with me. So our goal is moles per liter. Now, guys, what's step number two? What's our starting point? What's it say? Read it out of your notes. Mass divided by volume. So, guys, go to the problem and find a mass. Do we have a mass? Yeah. 7.2 grams of calcium chloride. Guys, I'm just going to give you the formula for calcium chloride. If you're still struggling with that, come and get support. Then, guys, the volume is 500 milliliters. So draw a line. Our starting point is 7.2 grams of CaCl2 and 500 milliliters. So guys, do you now see why we taught you how to do complex conversions? Like, remember the bicycle problem that we solved about Darrell Impey traveling some meters per second? How fast was he going in miles per hour? Guys, this is why we taught you that. Because we've got two conversions to make. We got to get grams to moles. Can we do that? Heck yeah, we can. You've been doing that for days. We can go grams to moles. Can we go milliliters to liters? Sure. We're going to do them both on the same line. So guys, let's start at the top. What do we need to know to go from grams to moles? Formula mass. Calcium is 40.1. Chlorine is 35.5 times 2 is 71.0. Then guys, you add those up. And the sum, which is then the mass of calcium chloride, is 111.1 grams per mole. So guys, what goes on the bottom? The 111 grams or the 1 mole? Oh yeah, you guys are learning this stuff, right? 111.1 grams is 1 mole. And guys, at this point, grams cancel. You're left with moles. We're done with the numerator. So now all we got to do is knock out the denominator. You may know how many milliliters are in a liter. If not, it's on the conversion chart, which is fair game for the test. But guys, it's 1,000. 1,000 milliliters is 1 liter. So what goes on the top? The milliliters or the liter? Milliliter, top to bottom. 1,000 milliliters is 1 liter. Then guys, the milliliters cancel and we're left with liters. We now have moles per liter. We're done. Now you just got to do the math. So guys, we've got 7.2. Be careful though, guys. This is the first time you've added denominator to divide by in your starting point. So it's 7.2 divided by 500 divided by 111.1 times 1,000. And guys, when I crunch the numbers, I get 0.1296 molar CaCl2. Go ahead. We're not done. Yep. So guys, now let's watch significant digits. How many significant digits are in 7.2 and 500.0? Well, this is 4 and that's 2. So that would be 2. 111.1 grams is 4. 1,000 milliliters is a liter, is infinite. Therefore, guys, we get 2 significant digits, and 1296 rounds to 0.13 molar CaCl2. You guys do, of course, understand the significance of this calculation, right? It means that my life just got infinitely easier because I don't have to mix solutions for you anymore. Guys, my life setting up labs is back in my lab hut with a balance and a graduated cylinder mixing your solutions. Because every time I make a solution for you, it starts with a solid and it starts with water. And I have to mix it at the correct molarity. I don't have to do that anymore. All I've got to do is tell you the molarity, and you can then figure out how much stuff to put in there. But we're not quite there. Because guys, all we've done right now is we've figured out the molarity. Now we've got to solve the problems like I just mentioned. Now we've got to figure out not what will the molarity be, but how do you make it? You guys ready to do the next type? It goes like this. So guys, write down the question with me. This one you're going to want to see. It goes like this. How many grams of NaOH are contained in 225 milliliters of 0.1 molar NaOH? So guys, these are the questions that now will allow you to make your own solutions. Because guys, this is what we're saying. Here is 225 milliliters of 0.1 molar NaOH. If you can calculate how many grams of NaOH pellets are in here, you can then make this solution. All I've got to do is give you a bucket full of NaOH pellets. You do this math, you figure out how many grams of NaOH are in here, and you can then make your own solutions. All I've got to do is give you a graduated cylinder and a bucket of pellets, and you can go make your own solutions. So guys, this is the last one we're going to solve of these type. It says how many grams of NaOH, which is a solid, are contained in 225 milliliters of 0.1 molar solution. So guys, dimensional analysis. What are we solving for? What are the first 6 words? How many grams of, that's our goal, grams of NaOH. Now guys, we need a starting point. And this is where you could get in trouble. Because guys, we've got 2 bits of information. We've got the volume and we've got the molarity. Where are you going to start? Never at the molarity. Guys, I would strongly encourage you to write this down. The reason that I'm asking you to write this down is so when you screw this up on the test, I get to take you back to your notes and say, I told you so. Because guys, if you get this wrong on the test, it's because you started at molarity. Don't start at molarity. So if you're not going to start at molarity, what's left? The volume. So we're going to start at the volume. And then we're going to draw a line. And now guys, we got to put our thinking hats on. How on earth can we get from milliliters to grams? This is some beautiful logic. What am I sitting on? Okay. Guys, how do we get from milliliters to grams? Where can we go first? Let me get you started. Let's go to liters. How many milliliters in a liter? You just figured it out a minute ago. 1,000. 1,000 milliliters is 1 liter. Milliliters cancel, left with liters. That's your head start. Now, guys, how do we get from liters to grams? Well, let's reason through this. Thinking about our moles conversions, we've got particles, we've got moles, and we've got grams. Now, this has nothing to do with particles. So it's a moles and grams thing. So, guys, this is actually the question. If we want to get to grams, what we've really got to figure out is how to get from liters to moles. Because if we can get from liters to moles, can't we go from moles to grams? Yeah, we can do that. So, guys, how do we get from liters to moles? If only we had a relationship between liters and moles. If only we knew a number that told us how many moles are in a liter. If only that existed. It's kind of the molarity, right? Because, guys, the molarity tells us what? How many moles are in a liter. So we're in liters. If we want to get to moles, guys, what's the molarity of the solution? 0.1 molar. What does that tell us? For every liter, how many moles? 0.1. Use it. For every 1 liter, there's 0.1 moles. Will it always be 0.1 moles? No, but it'll always be given. And now we're in moles. Did you like the little sarcastic twist there? So, guys, now that we're in moles, how do we get to grams? You better be able to do that. What do we need to know? Formula mass. Sodium is, liters cancel. Sodium's 23.0. Oxygen is 16.0. Hydrogen to 3 significant digits, because that's what our starting point has, is 1.01. Then, guys, we add up all of those numbers, and we get 40.01. So 1 mole of NaOH is 40.01 grams. Guys, at that point, we just got to do the math. So much so that let me just do it for you. So you've got 225 divided by 1,000 times 0.1 times 40.01, and that works out to 0.900225 grams. But now we've got to do significant digits. 225 is 3, milliliters to liters is perfect, 0.100 moles is 3, 40.01 is 4. So is that 3? 3. So that number to 3 significant digits would be 0.900 grams. So, guys, here's what that means. If you want to make this, if you want to make 225 milliliters of this 0.1 molar NaOH solution, all you got to do is weigh out 0.900 grams of NaOH pellets, dump it in here, fill it up to 225, give it a shake, and you're doing lab. You get the idea? Okay. So, guys, this is where we call time out. We've now done everything with molarity that you need to do. Thoughts about the concepts, the math, any of this? Y'all good? You're okay? Okay. So now we're going to do empirical formulas. What do you know about empirical formulas? They don't have anything to do with what we just did. You guys ready to hit the reset button? Okay. Guys, we've got about 6 minutes left and we're done. This goes fast. Empirical formulas. And by the way, this is the lab that you're going to do next time. Let me define it for you. Guys, an empirical formula is the simplest formula for a compound. It's simply that simple. See what I did there? That's all you need to know. It's the simplest formula for a compound. Now, guys, once you've written that down, I'm going to switch to a different slide, and I'm going to show you what this means. Please don't write down what's about to come up. You guys ready? Okay. So, guys, let me offer you some formulas for compounds. Some of these are familiar. Ready? You guys have probably heard of ribose, which is C5H10O5. Don't write it down. Maybe, depending on your biology background. You certainly have heard of glucose. Guys, this is the fuel that we burn when, well, yeah, you guys know it's sugar, right? C6H12O6. So is ribose. Ribose is also a sugar. But guys, maybe you've heard of lactose. Where do you find the sugar lactose? In milk. Some of you are lactose intolerant. You can't drink milk. It means you don't have the enzymes required to break down this sugar. This is C11H22O11. Now guys, these are all sugars. Do you see the pattern? What's the pattern? Yeah, twice as many H's as C's and O's. So guys, what is the C to H to O ratio? 1 to 2 to 1. So guys, all of these sugars share the same empirical, remember that means simplest, empirical formula. It's CH2O. You ready for the aha moment? Guys, these are all sugars, but sugars are a part of a class of compounds called carbohydrates. Huh? Oh my. Guys, that's where the name comes from. Literally, sugars, which are carbohydrates, can all be simplified to a backbone of carbon surrounded by water molecules. Carbohydrate, get it? Although it's not quite that simple, because the waters actually break apart and you've got an H on one side and an OH on the other, and these OHs and H's just spread down the molecule. So it's not really water molecules attached to the carbon, it's an OH on one side and the hydrogen on the other, but it still simplifies to carbon and water. That's why we call them carbohydrates. So guys, the big idea here is that all sugars have the same empirical formula, which is that. You okay? Now guys, if you know enough about biology, you may be thinking that I'm a liar. Because you're going, wait a minute, I know of some sugars that are not 1 to 2 to 1. The reason is because some sugars are what are called cyclic sugars. And what they do is they're long carbon molecules surrounded by the H's and the OH's, and they wrap together tip to tail. And when the tips and tails bond together, they actually eject a water molecule. And so the 1 to 2 to 1 ratio isn't exactly set. But if you were to break that apart and put the water molecule back, then it would return to the 1 to 2 to 1 ratio. It's all about chemistry. You guys good? Okay, so guys, here's what you've got to be able to do. You've got to be able to calculate these empirical formulas. And this is the way that you do it. Again, I'm going to give you steps. You ready? So guys, the steps go like this. Step number 1, and this makes no sense to you at all, but it will. Use the percentages as masses. Step number 2 is to convert your masses to moles. You can do that. Step number 3 is divide by the smallest number of moles. Again, that means nothing to you, but it will. And then guys, step 4 is write the empirical formula. So guys, here's how this goes. You take chemistry for me or Miss Call, you decide you like it, and there's that fateful moment when you decide, I want to be a chemist. So you go off to college and you get a degree in chemistry, and you find out that there are 11,000 jobs available to chemists, because there are, and you decide that you want to come back and live in Utah County, and you find a job as a chemist in a little analytical chemistry lab somewhere down in Provo. And one day this guy walks into your lab, could be a lady, doesn't matter. Somebody walks into your lab and they're like decked out and full on like construction stuff, hard hat. They've been out in the field for days. And this guy walks in and he goes, "We're in trouble. We're down there by where Geneva Steel used to be, and we stand to make hundreds of millions of dollars building homes." You know this is going on currently, right? But they say the problem is that we started digging around to start building basements on these homes, and we hit this patch of stuff. And we're afraid that that patch of stuff could be something that the Department of Environmental Quality won't allow us to put houses on top of. And if that's the case, that land just became worthless and it's going to bankrupt us. Tell us what this stuff is. And then he hands you a Ziploc bag full of white stuff. And you're going, "Oh crap." So your job is to tell this guy what this stuff is. Well, how do you do it? Well, guys, what you do is you take that stuff and you put it in what's called a combustion analyzer. Literally, you burn it up. And when you do, you then pass the smoke through a series of chambers. And these chambers lock into all the things that made up the white powder, and it locks onto them and actually tells you what they are and how much of it there is. And this computer spits back to you a report of what's in the white powder. And guys, imagine, and don't write this down, imagine that that computer spits back to you this. Whatever powder this is, it's roughly 33% calcium, 40% oxygen, and 27% sulfur. The problem is if you turn back to the construction dude and go, "Look, it's this." He goes, "That doesn't mean anything to me. I don't know what that is." So we've got to figure out what it is. Guys, do this with me. What is step number 1? Use percentages as masses. See, guys, this tells you percentages. What we're going to do is we are going to assume that it's a 100-gram sample. And if this is a 100-gram sample, then 33.3 grams is calcium, 40 grams is oxygen, and 26.7 grams is sulfur. Guys, notice the way that I set these up. One beneath the other. You should do that too. It's going to make your life a whole lot easier. Guys, set these up in columns. If you need to switch to the back of your page, do. So guys, that's step number 1. Take your percentages, use them as masses. So guys, what then is step 2? Convert to moles. And guys, you know how to do that. You just need the formula masses. So I'm just going to run through it. 40.1 grams of calcium is a mole of calcium. Do the math. 16 grams of oxygen is a mole of oxygen. Do the math. 32.1 grams of sulfur is 1 mole of sulfur. Do the math. Y'all caught up? Not yet. So guys, here's what we now know. Whatever that substance was, there's a 0.8 to 2.5 to 0.8 mole ratio. In the same way that carbohydrates are 1 to 2 to 1, whatever this compound is, it's 0.8, round numbers, 0.8 to 2.5 to 0.8. The problem is that we can't write a chemical formula from this because we need whole numbers. You can't have 0.8 of a calcium, 2.5 oxygens, and 0.8 sulfurs. We need whole numbers. So how do we get whole numbers? What does step 3 say? Divide by the smallest number of moles. So guys, of these 3 numbers, which is smallest? Top, middle, or bottom? Top. Divide by it, divide by it, divide by it. Divide them all by the smallest number. Now you ready? What's any number divided by itself? 1. What's 2.5 divided by 0.83? Functionally, it's 3. It's not exactly 3, but it's so stinking close given the accuracy of our measurements, it's 3. Then guys, what's 0.832 divided by 0.830? Functionally, it's 1. So guys, we've got a 1 to 3 to 1 ratio. Just like in sugar, we had a 1 to 2 to 1 ratio. Here we have a 1 to 3 to 1 ratio, and we can write the chemical formula. 1 calcium, 3 oxygens, 1 sulfur. Boom. So you go back to construction dude, and you go, hey, yo, construction dude, this is CaO3S. And construction dude had me for chemistry, and he goes, that isn't even a thing. And you're like, yeah, you're right, it's not. So then you got to figure out what it is. So guys, you can't name this. You learned a ton of stuff in the last unit about naming compounds, and you can't name this because it doesn't exist. So how could you rearrange it so that you could name it? Well, guys, when we write compounds, what always comes first? The metal. So the metal comes first. That's calcium. Then, what can we do with 3 O's and an S to turn it into something that we know the name of? SO3. Aha! Now you can go back to construction dude and go, hey, go build your houses. This stuff is just calcium sulfite, which is completely benign. Go to town, make your millions. So now you're thinking to yourself, how are we supposed to know that? Right? Guys, here's the deal. If there is a metal in your empirical formula, what does that make it, a salt or a molecule? Hear this, Ford. If there's a metal in your formula, is it a salt or a molecule? It's a salt. Put the metal first and then rearrange things so that it's something you could name. What if there's no metal in your formula? Then it's a molecule. And guys, at that point, you can write whatever you want because we haven't told you the rules about how to structure molecules. Get the idea? So guys, any questions about empirical formulas? You guys good? Okay. So guys, homework assignment number 4. This is the last thing that will go on your 4th quarter grade. It is on the back of this sheet. Guys, what you're going to find is that the first 8 questions are the molarity problems, separated into their 2 types. Then the last 3 are empirical formula problems. We will grade this next time in class. We will then do a lab where you'll actually be figuring out the empirical formula for a compound. Then guys, after the long weekend, we'll do another stations activity, which will be wonderful preparation for the next test. Please remember guys that the lab, the second stations activity, and the test all go on 4th quarter's grade. The only thing that stays on 3rd quarter's grade is the homework that you're now going to spend the rest of the class period doing. So we've got about 15 minutes. Guys, dig in. You should get a lot of this done. Another sheet of paper, starting points, goals. Guys, do this carefully and methodically, and let me know if I can help.